Next up is Duncan, who will be continuing to regale us with the joys of photosensors. For mice, if you missed it earlier, was it earlier this year? I've lost track. Some time ago in the past, Duncan gave us a talk about the use of photodiode sensors on small robots, and this is a follow-up talk to that.
So this is more or less systems level stuff. The other stuff was mostly electronic stuff. So the first question is, what ADC resolution do you need and how fast should it be? Speed is the important bit. If you've got a 24-bit ADC that takes 10 milliseconds to take a reading, it's a waste of time. You want the fastest ADC you can find. If you've got a serial interfaced ADC or something like that, with takes hundreds of microseconds to take a reading, don't. You really want on-chip ADCs. Okay, so this is what you can get hold of on the chips. You can get 10 or 12 bits, obviously. 10 bits will give you numbers in the range 0 to 1023. 12 bits will give you up to 4095. They look like big numbers, but they're not. And you must have a dynamic range that will allow for ambient light. So if ambient light takes you beyond these numbers, your chance of working at all is negligible. So ambient light is a serious issue that I'll be coming back to you. This was my arithmetic error. You can see, well, I've got 10-bit ADC. So your closest distance, which I've set here to 10 millimeters, the signal coming back from your light source wants to be about 512, a reading of about 512, and the other 512 is to allow for ambient light, because your ambient light can be at least as big as your signal light. It's an inverse square law, so you can see these numbers go down pretty rapidly. And at 160 millimeters, where I would like to be able to see a wall, there isn't much of a number there. So, 10-bit, people do use 10-bit ADCs, but I'd strongly recommend you use a 12-bit ADC if you can get your hands on one. That would be something to do with your choice of chip. So what can you do if the numbers aren't big enough? No. Digital signal processing theory tells you straight away that if you take two samples and add them together, that will give you an extra bit of resolution. So you can make a 10-bit into an 11-bit ADC by reading it twice and adding the numbers together. I've got a rather posh oscilloscope at home that uses exactly that to go from an 8-bit oscilloscope at high speed, at the 100 megahertz level, down to a 12-bit oscilloscope at lower frequencies. And it's doing exactly that. It's taking the average of the signals, but it's doing exactly that. So if you want to make your 10-bit ADC into a 12-bit ADC, take 4 measurements and add them together. But if you're making one conversion every microsecond, it's going to take you 4 microseconds instead of 1 to do that. In a similar way, you can make a 12-bit ADC into a 14-bit ADC, or anything you like. But if you want to add 4 bits to it, you're going to need to take 16 samples. It's going to take you 16 times as long. So if you find you're running out of numbers, this is a quick fix. You can make the numbers 2 or 4 times bigger just by taking multiple readings and adding them together. So just to tell you my favoured thing, I favour the STM32F072, which is a 12-bit 1 microsecond ADC. I find that pretty good. Okay. There it is. Right. The drivers, I guess most of you are using library drivers for these kind of things. Have a good look and see what they actually do. Some drivers will do a complete initialization of the ADC every time you try and read it. So it'll set up the I/O pin, it'll set up the clocks, it'll set up any multiplexers, all that kind of thing, every time you use the ADC. That takes a lot of time, not a good idea. Have a good look into what you do. More typically, drivers will do what my driver does. It takes a channel number and then it reads the ADC with that channel number. Now, if you're using the system I just described of taking multiple readings to give you more bits, the setting the channel number is irrelevant. So what you need to do is set the channel number before you turn the LED on, read the ADC, turn the LED off, so it looks a bit like that, pseudocode. Yeah. So instead of having a read ADC, I don't know, ADC brackets channel number giving you a value that you put into a variable, you need a function that sets the channel number, which will be typically a write to a register in the microcontroller somewhere, and then another function that just reads the ADC, and that function can be faster. So the LED is on for less time, takes less power, more safe, all that kind of stuff. And then when you want extra resolution, you do that. So you set the channel number, turn the LED on, read the ADC however many times, turn the LED off, and then add the readings together. You need to be very aware of what your compiler does, because this looks to be the same thing, and some optimizing compilers will only do it once. So know what your compiler does. There's a whole load of stuff that I talked about in the first section about the speed of things. And things get interesting between when you turn the LED on and when you turn the LED off and what your hardware is. So you want that time to be as short as possible. So you want your software to do the minimum between turning LED on and turning it off. And this is what I would recommend for that. So I've jumped over quite a lot of stuff there. Are there any questions so far?
Well, one question then, which is, the starting premise was only over 512 from the
At the close range, yeah. Yeah.
Which seems to me quite a lot of headroom for ambient light with something that needs to be region. Because some of the parts are quite a lot of light, so they seem to me quite good.
Yeah. You remember Worcester last year, was it? Where they had sunlight on the cores?
Sorry,
When they had sunlight on the cores? Yeah, the ambient light there was pretty strong. Yeah. I like to think in terms of leave the ambient having half of it. Yeah. Yeah.
I guess it's because of the distance of driving that far, but the further away it goes, or
Yeah. Yeah, but my example there was at the biggest signal position, as close as you're going to be working. So when you get further away, it's a lot worse. The ambient is many times the signal level. Yeah. Okay. So I'm rattling on a bit here. Let's keep going. All right. So you were talking earlier on about not having enough ADC channels, right? Well, here's some solutions for it. So a lot of boards only got a small number of ADC channels. Some of the Picos only got 3, something like that. Yeah. And sometimes when you're trying to build a half-size mouse or something like that, you just haven't got the pins. You want to use a board that's only got 12 pins, and if you've got 6 channels of sensors, which used to be common on mice, and you need 6 LED outputs and 6 analog inputs, that's your 12 pins gone before you've done anything else. So you need to be able to multiplex. So this is one side of a 6 sensor mouse, say. The green ones are the LEDs, pointing in probably relevant directions. Somebody else will correct me on that later. And the purple lines are the field of view, the 60-degree field of view of a flat sensor. And you can see straight away that this sensor can see the light cones of all 3 LEDs. So you can use the same sensor for looking at a wall that this LED can see, and a wall that this LED can see, and a wall that this LED can see. Yeah? So the software for this is turn this LED on, read the sensor, turn this LED off, turn this LED on, read the sensor, turn this LED off, turn this LED on, read the sensor, turn this LED off. So you've got 3 channels with 4 outputs driving the LEDs and 1 input reading the sensor. Okay. The disadvantage of this, because of this wide field of view, the sensor is exposed to more ambient light.
Presumably you only need to do 1 ambient light measurement though.
Oh yes, yes.
Rather than separate one for each.
Depending how fast it is,
Well, if you pass it.
you could do 1 ambient light sensor either before or after. If you're really worried about it, you can do 1 between each. But that's a simple software decision. Yeah. Remember, the individual LEDs are only going to be on for the same length of time they were going to be on for anyway. So exactly the same LED drivers you already had, and it's exactly the same sensor circuit that you already had. Of course, a mouse is going to want sensors both sides. So for 6 sensors for a mouse, you can do the same both sides, and that's going to give you whatever that is, 8 I/O pins, which is better than 12. But of course you can do better. Of course, nowadays some people only have 4 sensors. Is that typical now, Pete?
It's common.
Yeah. But with 6, used to be the case. So you can do better than what I've just described. Whoops, hang on, go back a bit. You can connect the 2 sensors in parallel. Because only 1 LED is on at a time, you only need 1, sorry, you can connect both sensors in parallel and look at everything. Again, you're going to get more ambient light. But it means you can reduce the ADC channels down to just 1 ADC channel. And I suggest if your microcontroller hasn't got 1 ADC channel available to you, you shouldn't be using it. But we've still got a lot of output channels for all these LEDs. So what we can do, we can disconnect the 2 sensors, so we've got 2 separate analog channels now, and we can turn on this LED and this LED at the same time. They can be mounted in parallel. So you turn those 2 LEDs on and take a reading each side. You turn those 2 LEDs on and take a reading each side, and you turn those 2 LEDs on and you take a reading each side. You're down to 5 I/O pins. Of course, if you've only got 4 sensor channels, like a modern mouse, you only need 4 I/O pins. And now you can use a controller board with only 12 I/O pins. You've got 4 for the sensors, 2 for odometry, 2 for PWMs, 2 for serial comms, and 2 for power. So you can use a very small board and still get a 4 sensor mouse. Okay, any questions on that bit? Good. Am I preaching to the converted? Does everybody know all this stuff?
Well, no, that's good. If you actually want to see some of this stuff in action, you can look at our HAL and the diffusion. Both of those use all of those techniques.
Great, yeah. I've got it on some mice.
So it works. It works, absolutely. It works. Yeah, no, it does work.
Okay. So now we're talking about the optics. This is the bit that messes me around most. I don't know about the rest of you, but getting the things seeing what they should see and nothing else is a big challenge. Obviously here we've got a sensor, that yellow thing, mounted above the LED. There's the floor, and we're trying to look at a wall over here somewhere. But in order to get the wide angle of the sensor in a horizontal plane, we automatically get a wide angle in a vertical plane as well. So we've got all of this ambient light would be incident on the sensor unless we put something in the way, a blind. Now you can, with blinds, you can manage the viewing area of the sensor very closely. And you can use mirrors if you want to do more complicated things, and you can use lenses if you want to do really complicated things. But blinds are the one that matters mostly. Now you've got to, it looks like, okay, I'll just put something in the way. And the obvious thing to put in the way is a bit of printed circuit board. Printed circuit board is not opaque. If you want to use PCB here, make sure it's covered in copper, because the light will go through the standard PCB. Maybe not very much of it, but enough to mess you up if your blind is between the LED and the sensor. So if it's printed circuit board, make sure it's got copper on it. Some printer filament is opaque, but a lot of it isn't. I don't know of any 3D printer resin that's opaque, because it doesn't work as a 3D printer resin if it's opaque. It's got to let UV through. Some black paint is opaque enough. Tipex is surprisingly good and it dries quickly. I normally use bits of dense art paper stuck on with super glue.
Even black paper often isn't.
Sorry?
Even black paper is often isn't very opaque. Surprisingly.
The stuff they sell as craft paper,
Yeah.
you know, the stiff stuff is pretty good.
I bought a roll off Amazon and it's like transparent, but it's red level.
I've spent a lot of time messing with this stuff. On Wednesday I was fighting this stuff. I was the latest wall follower, right? The sensor that does my positioning off the left-hand wall. I couldn't. It wasn't behaving itself. So I ended up sticking another bit of craft paper on there with super glue, and that solved the problem. I'll probably come back to that in a bit.
If anybody wants to do the opposite and wants to block out visible ambient light and only allow infrared light through, if you can still find it, get some colour film, 35mm colour film, expose it, have it developed, and it's a perfect infrared filter. Right? It's almost opaque at visible light, transparent to infrared.
Cool.
So is Coca-Cola, but that's not convenient.
You can get a lot of sensors that have got IR filters already in them, but presumably if you put enough layers of Coca-Cola, it will work.
It's
Frozen.
When you crash, it grows everywhere.
It's in the electronics. I'll try this.
Shall I close the door? If people are getting cold.
Yeah.
I'll just close that door.
Okay, simple single word slide, massive topic. So in principle, if all of the light from the LED is reflected off a wall, so none spills over the top or the bottom, and that all of that reflection is in the field of view of the sensor, you've got an inverse square law. Straightforward? Okay. The things that screw you up, any direct light path between the LED and the sensor messes that up. I've spoken about that. Any reflections off the floor mess it up. Any light spilling over the top or bottom of the wall messes it up. If you've got the problem of leaking light from the LED to the sensor, what I do is hold the mouse in the air, so it's at least a metre from anything, like pointing out this way, and read the numbers and see what I've got. If you can get that down to 0, you're doing extremely well. Right? But that's leakage light there. If you try and do the same with the mouse on the maze, you'll get reflections off the floor, which will look exactly the same as light leakage. And that could be an argument for using a test maze that's got a black floor. At short ranges, it can be tricky to ensure that the sensor sees all of the reflection. Right? Because the field, I dealt with it in part one, the field of view of the sensor and the light cone from the LED, they can't come from the same place. They've got to be spaced apart. So you've got one cone from there, one cone from there, and if you get close enough, you can't see all of it. So these things tend to happen at short range and long range, and you can get linearities there. So, but in the middle place, it's an inverse square law. So it's worth thinking about what we want this sensor to do. There's two things it's doing. One is positioning the mouse relative to the wall. Yeah? That's the thing we all think of. And the other thing we want to do is see if there's a wall there or not. Now, positioning the mouse, if you've got good mouse control, the mouse will always be damn near the same distance from the wall. And the linearity of the thing doesn't actually matter. You can just take the raw data and it'll be linear enough. But if your mouse is sometimes close to the wall and sometimes quite a lot further away, compensating for that inverse square law could be a good idea. But it's going to cost you some time. You're going to have to do a square root and an inversion. If you've got a fast processor, it's probably worth doing. If you're struggling with something a bit slow, just take the raw data and it'll be good enough, providing your mouse stays the same distance from the wall. When you're too close to the wall, all you want to know is you're too close to the wall. And when you're a long way away from the wall, all you want to know is there a wall there? And linearity doesn't matter, but sensitivity and consistency does. So when you're looking at a wall a long way away, you're usually just comparing the reflected light to a threshold. Yep. So linearity is important for mouse positioning, and if you don't get that right, your PID controller will have that non-linearity built into it, which is a pain, and it can, because it changes the gain, it can cause your system to go unstable. But you make your own choice as to whether you put in the square rooting and then the inversion. It's not strictly necessary. Okay. Testing. Test, and test.
Just a quick question about linearity before we move on to that.
Yeah.
It used to be a case with, particularly audio amplifiers and things, you use non-linear logarithmic plots and whatever to compensate for volume changes.
Yeah.
Is there an equivalent for an ADC, where you have non-linear ADC, a logarithmic ADC, which would compensate for that?
There is exactly that. The things they used to use in telephone systems had a mu law, I think was one of them, which was a sort of logarithmic thing, and an A law was a different one. Yeah. So they had sort of non-linearity laws. They're nearly all serial devices. They're all fairly complicated and they're quite old hat. So you're not going to find one of those built into a microcontroller. But remember, if you've got an ARM, I don't know, 26 or whatever the latest version is, running at the low terahertz range, linearizing it in software is not an issue.
I was thinking more to compensate for the range issue, because then you could use a 10-bit or something. If it's non-linear, then you might get a lot better at a distance than your two with that.
You could. The photodiode helps with that compared to a phototransistor, because they tend to have a large dynamic range, but then you have to compensate. Elsewhere, with an equivalently large dynamic range in your ADC, you could build yourself a logarithmic amplifier, okay, which is not a complicated circuit, but I would question whether it's worth putting one on the board for that, for that much gain, so to speak. But a logarithmic amplifier is not a terribly complicated thing.
It's basically an op-amp with a transistor in the feedback.
I suppose if there's a separate ADC chip which would do all that for you, it might be worthwhile. Because you can get extra channels that way.
You run into the philosophical challenge. You know, do you make it perfect, or do you want to run it at the next competition?
It's not so philosophical. It's
I think Paul has given us the exact demonstration of that problem.
If you want to do if you're concerned about the calculation, and you have a kind of gaming geekishness about you, Doom is famously the source of a fast inverse square root function. Look it up. The fast inverse square root function is infamous. You can find lots of details about it, and it's very quick. But to be fair, if you've got a decent processor that's got a floating point unit on it, just get on with it.
Or you could just use a table, just calibrate it at different distances and look it up and convert it into a...
It wasn't so much the software side of it I was worried about, it was more the ambient light overload, overrunning the overloading sensor.
Yeah, you're exactly right. By the time you get to the software, all of the dynamic range has been determined. Yeah, it's too late there.
Duncan makes a very good point in that it only has to be linear enough over the expected operating range. And one of the fundamental rules of all of this game is if you don't want to be correcting gross errors, don't make gross errors.
Trying to avoid crashing into walls, is that what you're saying?
Don't put yourself in a position where you could crash into the wall in the first place, rather than trying to avoid crashing into it.
Just as the single precision doing one is good, but you're exactly right. Some games, if you're on a 3D game, then things like the Doom single precision hack is good. But a lot of the older games that you just think they're just treating each bit of the signal as linear, and then you just table to D. You know, it's sort of half D linear of half D log D. It's fast enough for 8-bit games. So
I mean, strictly speaking, what's it? A lookup table for a 12-bit ADC only got 4,096 elements.
that's true. So
And
you
it
can
runs
whole
fast,
big.
you know.
Yeah.
We're not running on 8051s anymore.
I'm running on a Z8.
Speak for yourself.
So this is how I test. So I've got my mouse with sensors on. I've got my piece of wall. The spacers in between are lasered out of MDF. And I've got spacers for 5mm, 10mm, 20mm, 40mm and 80mm. So I can do 0 to 155mm by slipping these things in. And the nice thing about this is it holds the wall at right angles to the sensor. Which is another whole can of worms, which I had planned to talk about a bit, so I will. When you... That's going to sound good on the microphone, I'm afraid. That's the same pocket. Okay. So you've got your light beam from your sensor, and if it comes onto the wall at right angles, you're going to get a mirror reflection back into the sensor. So if the wall is at all reflective, that is going to give you your maximum signal, and when you go at an angle, it's going to give you less signal. In theory, if the wall doesn't have any mirror reflection, and so the amount of reflected light is independent of the angle, when you turn the relative to the wall, because the spot of light is finite size, some of the wall that your spot of light on is closer to you and some of it is further away in equal amounts. And the stuff that's closer to you gives you a bigger signal than you lose by the thing that is further away because of the inverse square law. So if this doesn't reflect like a mirror at all, you're actually going to get a minimum at that point. And that's a good way of testing how reflective the wall is. Practical walls, they're always going to be bigger at that maximum point. So if you want to test angles, you want to think about it very carefully, and you probably want to rotate about the front face of the wall, not the middle of the wall, because otherwise you'll get yourself confused. It's the front face, the angle of the front face that matters, and when you rotate the whole thing about the middle, it's slightly different, I think. Right. Test as many wall surfaces as you can get your hands on, because you don't know what you're going to come up against today, except for me, because I do, because I keep the walls. Yeah, thank you for that. Yeah. When you do the testing, you're probably going to find you want to tweak the range of the sensor. When you tweak the range of the sensor, tweak the receiver. Right? Always run the LED as hard as you can. You want the maximum light out of your sensor that you can get, and you desensitize the receiver to adjust the range. That is going to give you the best ambient rejection, your best chance of doing that. Right, am I out of sync yet? Okay. This is an interesting question. I've talked about, I'm not the person to ask about this, by the way. There's plenty of other people here who know far more about which way the sensor should point than I do. Right? But I mentioned briefly this business about you don't want them to point straight at the wall. If they're near pointing straight at the wall, you'll find you've got a much better angle sensor than range sensor. Yeah? The front ones will typically point straight ahead, sometimes slightly outwards, sometimes slightly inwards. Right? And the temptation is to make them point horizontally at the wall. Okay? But then you get the problem that you're very likely to get this mirror reflection. And there is a trick to that. You could point them slightly downwards so that the reflection misses below the sensor, or slightly upwards so the reflection misses above the sensor. That make sense? Everybody got that? Good. Right. Wait a minute, am I dealing with this yet? The problem, of course, is when you want to look at the wall a long way away, if you tilt it down, it's going to see the floor, and if you tilt it up, it's going to see whatever's above the maze. So there's a limit to how much of that you can do. So looking at a wall a long distance in front of you is a bit of a challenge, but very worthwhile. What else have I got? You want to keep the light source and the light sensor as close together as possible, because that gives you the best chance of missing the reflections. The bit about where you mount the sideways pointing sensors is something that I think is open to a lot of discussion. When you're talking about a wall follower, which is what I probably know most about, the angle and position of that sensor can determine the performance of the mouse. Absolutely. Moving that sensor a millimetre forwards can lop milliseconds off your time. Changing the angle will lop significant amounts of time off your lap time. Right, what goes on? If you've got your sensor pointing at a shallow angle, the gain in the PID system in terms of how the apparent range changes as the angle of the mouse changes is very high. So a tiny change in angle will make a big difference in the range you see. If you're coming at a more sensible angle, that changes, and if you're head on, the range is almost independent of the angle. So there's some kind of tangent law or something like that. Yeah? So that has an effect on your PID system. There's also stuff for maze solvers. If you're running at a shallow angle and you come past the edge of the wall like that, you're very soon going to be at the point where you're seeing this wall here, not the wall in front of you, but the wall off to one side, at an awkward time. So you certainly don't want it too shallow from that point of view. But on the other hand, on a wall follower, you might want it quite shallow. Yeah. So think about it a lot. Talk to people who know a lot more about it than me, and do your own experiments. But that is a serious problem. To the extent where some time back, Bernard and I were having long discussions about that and decided what we actually needed was a micrometer adjustment to get this angle right. Because you seem to be forever tweaking it. You couldn't get it right. Didn't matter what you did, it was wrong. Okay. Next thing.
So you have lots and lots of sensors on there.
Yeah.
I've seen YouTube videos of people that have put what their life was, they've put like an array of like 20 sensors around.
Yeah.
But presumably that's if they're a ball follower or a maze solver. Not. Is there any advantage to having, let's say, 4 in each corner and 4 in each corner?
The first solver I ever built had got an awful lot of sensors on it. I can't remember. I think it was 14. And one of them was in exactly the right place, so when it came off the edge of a post, the wheels were actually in the right place. If you stopped the inside wheel, it would rotate and be in the centre of the thing for the next thing. So I had special sensors just for that. It was covered in sensors. It was appalling. The big advantage of it, it was big. And of course, you get videos of the mouse in the maze. And I ran a business at that time called Swallow Systems. And I decided I needed something to shield the ambient light from all these sensors. So I made the maximum size possible umbrella, 25 centimetres square, covering the whole top of it with Swallow Systems written all over it. So that when this was trundling very slowly around the maze, it was just occupying advertising space. So yeah, there are other reasons for wanting to shield the sensors just than keep the light out. Yeah. Right, next thing. Mouse tilt. Okay, now this here, it's a pretty poor diagram, but never mind. This is the mouse on its wheels. It's a wheelchair. I've got 2 millimeters clearance on the slider here. You've got to have something like 2 millimeters clearance minimum to get over the changes in angle of the maze bases and bumps and humps and goodness knows what else. Right? And I've set this up here now, so that with that 2 millimeter clearance, at the long range wall, I'm in the centre of the wall. Okay. Now the trouble is when you decelerate, you lose your 2 millimeters clearance here, and this is now spilling off the bottom of the wall. So that influences the mouse design. The mouse can be front heavy or tail heavy. That's a personal choice. Most people try and get them as balanced as possible, but they will always be heavy one end or the other. My recommendation is that they are front heavy. This sounds counterintuitive because it means getting over the bumps is harder. But it means that when you brake, you're in this situation and your light beam is going to go where you want it to go. And it's during braking that you're most interested in getting an accurate measurement of the wall in front of you. When you're accelerating hard, I assume it's because you know there's no wall in front of you. Otherwise you're going to break my walls. Please don't do it. So front heavy, and then you'll know where your light beam is pointing during deceleration. And during acceleration, if it's not quite where you want it, maybe it doesn't matter quite so much. Okay, okay, right. So sometimes you just want to see if there's a wall there somewhere in front of you. Ideally, you'd want to be able to see 4 cells or 8 cells in front of you. You're not going to be able to do that. But if you can see far enough in front of you with a wall follower, there's no point learning the course. Because if you can see the gap in the wall or the wall in front of you far enough away to brake from your top speed, you gain nothing by learning the course. So range extension is valuable. I'm not saying you can see 4 cells in front of you, but that's a different issue. And my pointer has just fallen apart, so let's hope it's going to work. Okay. So we talked about this multiplexing business. Now there's a trick you can do here. So what we've got is 2 wide angle sensors and 2 narrow angle LEDs. Okay? If you want to see as much as possible, you turn both LEDs on at the same time and you take both sensor readings. So each sensor is going to see 2 LEDs, you're going to get twice the range, twice the signal, and you add together these 2 and you're going to get twice the signal again. So in principle, this will give you twice the range. And it's free. Oh, what I didn't say, yeah. There's things you can do with the electronics. You can add more LEDs to the sensor. So with the conventional voltage switch, turning the LEDs on, you can just put more LEDs in parallel there with separate current limiting resistors. And every time you add an LED, in principle it's going to give you a 40% range increase. With my constant current driver, with a 9-volt supply, there's enough headroom to put 2 LEDs in series there, which just costs you the LED, and that will again give you that 40% range increase. That's what we're doing on the current Warriors wall followers. So we use 2 LEDs in 1 sensor. Okay. At this point, I have technically finished, and I've only overrun by about 10 minutes so far. Are there any questions so far? Everybody happy? I do have a bonus slide if you want it. Somebody tell me whether to... Okay, right. Too late, I'm committed now. Right. I've talked an awful lot about getting rid of ambient light. Ambient light comes in various descriptions. Sunlight is the easiest because that's basically DC, and it only changes if a cloud goes over it or if your mouse turns or something like that. So you don't have to worry about higher frequencies from that at all. The light from fluorescent lights flickers in the UK at 100 Hertz and in America at 120 Hertz. Incandescents are about the same. LEDs can flicker at any frequency, but fortunately the LEDs they use mostly for lighting systems have got a phosphor in them to convert a UV or blue light to white light, and those phosphors are pretty slow, so they don't actually flicker as much as they could. So the message is that the ambient stuff is at low frequencies, and the things that we want to look at are at high frequencies. Now this is an idea I stole from Dave Otten about 20 years ago. It's been used in his triangulation sensors for a long time. And what would we have? We have a photodiode here, and we have an op-amp as a transimpedance amplifier, and the bias is taken off the microcontroller supply. So that is our ADC reference, if you like. Yeah. So the current through the photodiode is applied to the negative input here. This is high impedance. It won't take any current. The op-amp it changes its output voltage to try and balance that back to whatever's on the positive input. So our current through the photodiode is going to be balanced by the current through this lot, and the op-amp will operate to make that current the same. Now, at high frequencies, this capacitor is a short circuit. So high frequency current through this resistor is bypassed to ground and doesn't get any further. So the only way the feedback current can get back to this point is through R1. That's 100 kiloohms. So that acts as our load resistance for the photodiode. So you can see for a 10 microamp change here, you're going to get a 1 volt change there. We can use a bigger resistor here than we can in the simpler circuits because the ADC is fed from a low impedance point here. Okay? So at high frequencies, it looks like a photodiode with a 100 kilo ohm load, and it's going to give you maybe 10 times the voltage that you would get with a 10 kilo ohm load, which is about the most you can use with the with a normal ADC input. Now, of course, at low frequencies, where all this ambient light is, this doesn't do anything. So we've got another feedback path through these two. And between them, they're about a kilo. So our 10 microamp photodiode current at DC only needs, whatever it is, 100 millivolts or something here to put the balance current back. So at low frequencies, you're actually going to get 100 times less gain from this circuit. So it acts as a filter against your ambient light. It's worth doing. If you've got one of these multiplexing schemes, so you've only got 2 ADC channels, it's only going to cost you a dual op amp and a handful of resistors and capacitors and so on. If you're using the dual op amp circuit, of course, this and this and this and this can be common to both channels. So it doesn't cost you a lot of weight and size and costs. I used a TLC 272 here, which I think is about 50p or something, dual op amp. Now, unfortunately, the op amp isn't a perfect op amp, so it's a bit slow. It's got slew rate limitations, it's got gain bandwidth product limitations and all the rest of it. So it slows down the response a bit, so it's going to take a couple of microseconds to get to peak signal. So you're going to have to balance that in your software. You put a small delay in, just like I talked about in part 1. And just to chuck some numbers on that, when I measured it, the response I got at 10 kilohertz, which is sort of what we're interested in, was 20 times the response at 200 hertz, which is the sort of highest ambient light frequency you need to worry about. So giving yourself a 20 time reduction, whatever that is, 26 dB improvement in signal to ambient noise ratio is worth doing. It's not actually going to extend your range very much because we'd only allowed half of our signal range, whatever that's 6 dB, as ambient header, but it will improve the performance of everything. And that, I promise you, is enough.
Is that a burst order filter?
Yeah.
With like a, or is it 470 over about 200 hertz near something?
Yeah, well, it's the Thevenin equivalent. Andrea can probably tell you all about this. It's the Thevenin equivalent of those two, I think, into there. Yeah. The value of that, as long as it's big enough, doesn't actually make much difference.
Yeah.
It gives you 20 dB per decade.
Yeah.
Yeah, it's good stuff.
I got one question. If you're just
Yeah.
what's the effect of laser diodes versus standard LEDs?
They're bigger, they're heavier, they cost more.
Okay.
Right? Apart from that, what it improves is the spread of the light cone. Okay? So you've got more chance of keeping the laser dot on the wall. Unfortunately, if it goes off the wall, it's catastrophic. But it doesn't affect the inverse square law coming back again because the laser dot radiates in all directions.
Yeah.
So it doesn't, for the same light power, as long as the whole dot stays on the wall, it doesn't give you any improvement. But what it really does give you is a vast improvement in terms of spotting the edge of a wall. So you get a much faster transition as you go past a post. Because the problem with a dot of light, it's spread out. And it's actually quite difficult to measure the reflectivity of just a post because most LEDs will actually give you a dot of light that's bigger than the diameter, the width of a post. You know, the laser doesn't give you that problem, but the laser will give you a problem with seeing the slots in the posts. Yeah.
A laser typically of the kind that would be permitted and prepared to actually put on the actually doesn't have a lot of power. Compared to a device like the SFH 4550, which we use, which puts out actually quite dangerous amounts of light. And it really is illuminating the wall a lot. I would suggest you get a much, much bigger return from even a small spot LED.
But on the other hand, you've got a better chance of keeping the laser on the wall.
We're back to the catastrophic error.
Yeah.
Don't get yourself in a position where it's a problem. Which reminds me, at some point, an evening session, a good evening session, might be about things like the edge detection and feature detection, because whilst it is more difficult with a large spot, I have a whole kind of set of paraphernalia to find, and I can, at the moment, I can very easily see. You know the little slots? You can, even with an ordinary LED, you can see them.
I've got another question. I know everybody wants to come and say something, but is there any difference in the reflectivity, there are such specular reflections between near infrared and visible light on a wall, or is it marginal?
Get some walls and tell us.
Okay.
When I did my tests, I didn't notice any great difference.
Yeah. I mean, I've looked at if you use the Raspberry Pi camera without the IR filter, and I guess, I mean, I didn't sort of see, but I'm just wondering whether I've got a couple of different types of walls.
My suspicion is that the specularity is independent of wavelength.
Especially
It's to do with the surface roughness.
The frequencies are quite,
Unless you
they're
get
not
one of
all
those
that
funny
far.
kind of dichroic paint things that they've got on cars.
Yeah. Yes. Thank you.
We could make our walls like that.
Well,
Not pretty.
well, let's have walls.
So thank you very much, Duncan. There's a lot of
You're
good
welcome.
factual information there.
As I say, it should be available to everybody as soon as it goes.
We'll make sure that goes up one day real soon now, you know, given my state of my memory these days. When you're coming to build a robot, MicroMouse, a line follower or whatever, there are lots and lots of different ways that you can tweak the performance and things that you can focus upon. And I think some things have less room for maneuver than others, so the motors, you're constrained by what you can find and how you can drive them. The software clearly is going to have a huge influence, but after that, the sensors are a big, big component in the success of your robot. So if you're new to this, or even if you're not, be open-minded about how you can configure your sensors and how you can set things up. Okay, and there was one point Duncan made which is quite dear to my heart. The idea that their performance can be quite, I've lost my English now, their performance can depend quite a lot upon the angle of incidence, right, compared to the walls. And that's not just about the sensitivity, it's not just about the linearity, it's about, it tells you when you can reliably turn the mouse and things like that. I see people do it a lot, and I just caution you right now because it's on my mind. You may be tempted to go, well, if I just bend it forward a little bit or bend it back a little, don't do that. Okay? Find a place that works and epoxy it down. Because trust me, you will crash the mouse, you will pick it up, and if everything has been dependent on the last half degree of adjustment, it's all over. Right? Get something that works, stick it down firmly.